how to use strain gauges, okay, in dynamic fracture. So how familiar are you all with fracture? Fracture mechanics? Most of you? Okay. All of you are familiar with. How about United people? So okay, then I don't need to. So as you know, there are three modes of fracture. So mode 1, mode 2, mode 3. So mode 1 is that if I have a body which has a crack in it and I'm pulling it, so the crack then begins to open up. So that's opening mode. The other is that there is, let's say there's a body, there's a crack, then the upper half of the body I push this way, and the lower half I pull this way. So that is mode 2. So that's called in-plane shear. The third one is like when you tear a paper. So I then, if I have two, then upper half I move this way, the lower half I move this way. So out of plane, that's going on. So that's mode 3. And then, so what characterizes the stress field around the tip of the crack? What parameter is the, assuming basically linear elastic behavior of the material? What is the fracture parameter which describes the stress field around the crack tip? It's called the stress intensity factor. So the stress intensity factor is what describes the stress field around the crack tip. However, the stress field around the crack tip is a function of the inverse square root of the radius from the crack tip. So if I was to write this, so we can say that sigma, okay, around the crack tip is a function of, okay, it depends on 1 over square root of r, and so that's the inverse square root singularity. So what happens is then the stresses become, what do they become? They become infinite if I go very close to the tip of the crack. So if I have let's say I have a crack like this, and I am applying some remote stress, sigma infinity, let's say far from here, then if I, let's say this is R value, this is theta, then if this R becomes very small, I come right on very close or on top of the tip of the crack, then this gets to 0, then sigma becomes very big. But sigma cannot become infinity because you will have some plastic deformation. So there will be some stress relief, and that very sharp tip will become little rounded. But so what we do is generally the way we get around that is that we take a small portion here. If I avoid that portion altogether, so I say that zone is not, I will not go into that zone. So I'll avoid that zone. But let's say there is some zone here in which this singularity holds. So that inverse square root relationship is valid in not very close to the tip, but not too far either, because if you go too far away, then it is that 1 over square root r dependence becomes either inapplicable or very weak. So then we will operate in this region. So that's called the linear elastic behavior. And if you have a very small zone in which you have plasticity, so which is something like here, this zone in the middle, then so if that zone is very small, then we are able to still say that it is linear elastic fracture. And so most of the time you will see that sigma is equal to then given by k over 2 pi r square root and then some function of theta. And that k value is the stress intensity factor. So for any value, any point around that crack tip, but in that zone, for any point r and theta, sigma depends only on k. You don't need anything else. So that's what this k is the stress. So if you have stress, if you are doing mode 1, this becomes k with a subscript 1. If you have mode 2, then k2. Okay. So that you write k2. Mode 3 is k3. Like that. Okay. So now people use all sorts of different methods to study fracture in materials. So you can use photoelasticity, you can use method of caustics, there's interferometry, mainly Moray interferometry, you can use strain gauges, digital image correlation has become very common nowadays. So you can do all of these. Okay? So in this workshop we are going to do strain gauges today, and then tomorrow we will work on photoelasticity. Okay? But we will not be covering the other methods. So, by and large, moving crack is considered dynamic when inertial effects have a significant influence on the stress field around the crack tip. And this generally happens when crack speeds start approaching the wave speeds in the material. Okay. So, or probably about even half the wave speed, still these effects become important. When the plastic zone around the crack tip is small, the stress field in the vicinity of the tip represents a single parameter. Okay, so I already talked about that. But that's for the static case I was talking about. But when you have a dynamic crack in opening mode, moving at a high velocity, then we'll call that K1 with another subscript, which is D, to represent the dynamic nature of the crack. So it becomes dynamic stress intensity. So now let's first talk about isotropic material. Okay. So you have here a crack tip which is moving at some speed c. In this material the wave speeds are c1 is the longitudinal wave speed, c2 is the shear wave speed. And then in that case, now we attach, generally in fracture, we always attach the pointed axis to the tip of the crack. Then these are the equations of motion here. Now there are quite a few equations, and they are all listed, numbered, so you can later on look at those and try to work with them if you want. Then we have the stress-strain relations in the isotropic material, in the standard equations, we have those. Then in this case, then we substitute that 2 into 1 and using the definitions of dilatation and rotation. And then you work through some of this math here and you will end up with this equation. And then Irwin in 1980, okay. Now George Irwin, he's kind of considered as the father of fractal mechanics. In 1980, for a dynamic crack in an isotropic material, he said that the dilatation and the rotation can be expressed by this complex function. Now, how he came up with this? There is no explanation. He just came up with it. He said, yeah, this is what it is. So, in fact, there was one professor I knew, he was his PhD student, and he worked on dynamic fracture, so I asked him, what is the basis? So, before you knew, how did you derive this? He said, I asked George Irwin the same question, and he said, I don't know, I did not derive it. I just wrote it down. I thought this is what it should be. So, and till this day, people are still using it. Okay. So that's the way. So don't ask me how you came up with this. So then here Z1 and Z2, okay, are the velocity transform coordinates defined in figure 1. So these are these here. These are the velocity transform coordinates here, Z1 and Z2. So, and then there are some constants A and B, which should be B. So A and B are determined from the boundary conditions. Then you keep working through this, and you will ultimately come up with, these are the expressions for the strain, constructing strains using Hooke's law, the in-plane stress components on a plane. Okay. So these are the final equations here, sigma x, sigma y, tau x, y. I gave you some references for some papers on the very first introductory lecture we had. So you will find some more details in there, okay? But by and large, this is what it is. So now, my goal is to see how we start with strain gauges. How do we use those? Okay? So suppose now we got, this is the stress field around a crack tip moving at a velocity c in an isotropic material which has wave speeds of c1 and c2, and the crack tip and the axis system is attached to the crack tip. So that's what these stress equations are. Now they must satisfy the boundary conditions. So these are the boundary conditions for x less than a, y equal to 0. Okay. What does that mean? X less than a, y equal to 0. Now that's the surface of the crack. So on the surface, these stresses are 0. Away from the crack into the material, but on the x-axis, tau x, y is 0 because of the symmetric nature of the applied loads. So for this crack tip stress field, then we need to now define these complex functions gamma 1, gamma 2. They are defined as a series, okay, as a complex series. Now notice that the series, this z function, this z value has an exponent which has minus half in it. So when n minus half, when n is 0, what do you have? z1 to the power of minus half, which relates to this 1 over, this is r to the power of minus half. So the coefficient of that term will then become the k value. So that's purposely done like this. So where is this valid? This is valid close to the crack tip because in this small region around the fracture is where the inverse square root singularity 1 over square root r is valid. Okay. And it represents the stress field. Then, and that's what it says here, the leading coefficient C0. So C n equal to 0, then this bit is related to the stress intensity factor. Now, but we want to cover the stress field completely. So stress field, the second choice for these complex functions, because of the finite specimen boundaries, is that now we choose such type of functions which don't have an inverse square root. So they are representing stress field a little far away from the tip of the graph. And again, to satisfy the boundary conditions here, then this B value must be equal to this to be able to satisfy the boundary conditions. Now, so we have these two sets of stresses. So you superimpose them and you write them as joined together, and then this then finally becomes the stress field around the crack tip in an explicit form now. So you have now gamma 1, gamma 2, Z1, Z2 and all. Okay, so now we come to the strain part of it. So if I put a strain gauge here at a certain angle, and you orient now this rotated coordinate system to the strain gauge so that it aligns with the axis of the gauge. So the x-axis aligns with the axis of the gauge. Okay. And this is then our complex strain transformation, which you can find from standard mechanics books. And using Hooke's law, you can write out like this. So that's, then I now have the strain field around the crack tip. And if you now substitute the stresses in it, so this still has sigma x, sigma y and all those, and I have these stress fields from here. If you include those, then you get this big expression here, which tells you their strain in terms of only these complex functions. Then if you write out in terms of r theta, okay, all the complex variables, then you get this expression. So now I have only angles here, I have lambda 1, lambda 2, and all of these are already known in terms of the wave speeds and the crack speed. And then what else do I have? I have some of these constants, C1, D1. So those constants still have to be found. So it turns out that people have shown that C1 is generally equal to 0. Okay. For most of the dynamic cracks. Okay. There's some other papers you will find where they have shown that. Then the remaining term is this B term here. And that B term can be set to 0 if I have cosine 2 alpha equal to minus alpha here. Minus. So then that's your, so now all I need is this mu term, the Poisson's ratio. So if I write cosine 2 alpha equal to minus Poisson's ratio, then this term also drops. So we want some of these terms either to be evaluated or drop out so that I'm only left with the inverse square root term. So I can then easily find my stress intensity factor. So for a type of polyester called homoline, the new Poisson's ratio is 0.35, and then if you use this cosine 2 alpha equal to minus mu, you will get alpha is 59 degrees or 120 degrees. So what we are going to do now is that we are going to put that strain gauge around the crack tip at a certain distance and at that angle. You can put it at either 59.4 degrees or 120.6 degrees. One or the other. So also we want that the strain gauge is located in the singularity dominated zone, which is this one here. Okay. We don't want it to be too far out where the singularity doesn't affect the gauge. Then what we can still get some numbers probably out of it, but they are not accurate anymore. Now I do have here, let me see. See, so in a single edge notch specimen, which is this, that's a single edge notch specimen. So the notch or the crack is on the edge, not in the center. So that's it. And this is 80 millimeters. This 1 inch is, this bar here is 80 millimeters. So this zone you see here is the singularity dominated zone. So it's fairly large. Okay. But what you see here is that this is an obtuse angle, about 120 degrees. Then in that direction it extends much longer. But if you go in the acute angle direction of 59 degrees, it doesn't extend too far. So if you put the gauge outside too far, then it is not in the dominated zone. But if you put it too close, it will be in the singularity dominated zone. But what's going to happen if you put it too close to the crack tip? We have this zone, small zone here, which is having non-linear three-dimensional effects, whereas we are talking of plane deformation and plane stress type of deformation. So then you may again start to see errors. So you have to kind of see where you want to go. Okay. Now, if you use another type of specimen, which is this modified compact tension specimen, here this zone is, I think it's only 15 millimeters. No, 10 millimeters. This is only 10 millimeters. So that means this acute angle distance here is only about 2 or 3 millimeters. Here at least I still have, this is 80, so this is about 15 millimeters or so. So I'm still okay. I can still put a gauge a few millimeters away and still be inside the singularity zone. So this is the modified compact tension specimen. So what happens in this one? See, so you load the sample by pulling out here. So you push out that. And then there is this crack tip here, so the crack tip begins to open and it begins to move. Okay. So when it begins to move, you will see that there is a, what is there? A neutral axis somewhere here. So before that, it is opening mode, but after that there is compression. Okay. So the crack will begin to slow down. So that's the only difference. And this is the single edge notch specimen. So here then I can put gauges in acute angle and obtuse angle both and see which one gives me better results. So I can do it all in one test. How do you run the test? You have this here, okay, this crack. You need to sharpen the crack. You don't want that crack to be very blunt. So how do you sharpen it? So you first cut this crack with whatever tool you have, a bandsaw or some cutter or drill bit or milling cutter or whatever that is. Then at the end, you can either use a blade, a very fine blade, and make it sharp, or use a V-notch or something like that. Then when you start pulling this out, you start loading it, okay? So can talk later on. Thank you. So, so you pull this out And then what happens here? As you keep loading it, what happens? I'm increasing sigma, right? I keep increasing sigma. What happens to K? That also goes up. Right? Then there will come a point where that K cannot go up anymore. So it hits a critical stress intensity factor value. And after that, the energy balance in the system becomes such that, so as you keep loading it, the crack is stationary, nothing is happening in those assets. But what is happening? You are storing strain energy inside the cell. So keep putting it. The bonds are being stressed. Then suddenly, some bonds begin to break. And you create a bigger surface. So the crack extends. And so some of the energy is released into making the surface of the crack, and the remaining energy, if there is still left over, it goes into extending the crack more so that more energy can be absorbed. If the energy released is not enough to keep extending the crack, then the crack will extend a little, absorb all that energy which was released from the strain energy in the sample as surface energy of the crack. If the release of the energy is large, then the crack will keep on extending. It will become a dynamic and moving crack. That's when catastrophic failure happens, and you have now most likely exceeded the critical stress intensity factor. So that's how basically, and then the crack tip hopefully will go straight. Now sometimes in isotropic materials, it's a good chance that it goes straight. In composites, it's very difficult that it goes straight. So then you have, if it starts to angle out, then you have a problem with the strain gauge. So what can you do? So a lot of times what we do is, if you put the strain gauges on this side, on the back side, I make a little V notch. A very small V notch on the back side, okay, so that I guide the crack through that straight region. Okay, so we talked about this then, that we want to locate the gauge in the singularity zone, and then notice what happens here. So this is the obtuse angle gauge, 120 degrees. The crack velocity is 370 meters per second. The gauge, YG, is 7 millimeters. That's the height. That is this distance from here to here. From the expected path of the crack to the center of the gauge. That's 7 millimeters. And again, this is just a polymer, overlay polyester type material. Notice what happens, that when the crack tip is passing below the center of the gauge, you get the peak value of the strain. Okay. So basically this crack starts to extend. When it's here, the center of this gauge, it gives you the peak value. But notice here, now for the acute angle gauge, when it passes through the center, it gives you 0. Or not 0, but a very low strain out. It doesn't give you the peak. So the peak is somewhere else. So somewhere else means the crack has gone beyond the center of the crack. So there is this difference in the response of the gauge. Okay. Now so this is the relationship that defines the dynamic mode 1 or opening mode stress intensity factor, and we have all the values here we need alpha we know at what angle we put the gauge. YG I know, lambda 1, lambda 2 are related to the speed of the crack. So I know everything, and I am measuring epsilon x, that is the strain output from the gauge, by using some readout for the strain gauge. So I know everything. This is how the strain profiles look like. These are actual strain profiles. So that's the value of strain, microstrains. So you see with time as the crack is propagating under different gauges, I'm getting this. And that we already saw that. So I can easily go and find the dynamic stress intensity factor very simply by just putting a strain gauge. It's very easy to put a strain gauge. Okay. And just measuring the output from 3 or 4 different gauges. And so you can then take an average value, or you can know that as the crack length keeps on increasing, okay, as a function of the crack length, what is the K1 beta? Okay, how do we apply? Now you can do the exact same thing for an orthotropic like composite, where you have fibers either in 0 degree or 090 degree direction. Again, you go through very similar process. You find the stress field here, you write the equation below, then you try to come up with a solution which is based on, again, complex functions. Okay. And the wave velocities and crack speeds are known, and you then in going through this, again you use velocity transform coordinates for your transformation, and then ultimately you will come up with a stress field around the crack tip in terms of these complex expressions. Then you will keep going, apply the boundary conditions, apply very similar form for the series solution. One is the near field solution close to the crack tip, which has a -half exponent in there, and use a far field solution where you have no exponent. And then you will end up with, this is your second far field solution. See, there is no -half. And then you add all of them up and you get this big looking expression for the crack tip stress field. And then you end up with, now you can rewrite this whole expression by considering only the first term in the series solution. So we take n equal to 0, m equal to 0. Only one term we are taking, because that's what we really care about. Of course, if you don't take higher order terms, you will introduce some error. So people have done some work, they took second, third, fourth, fifth order terms, okay, and found out what is the difference between only using the first order versus up to the fifth order. And then they found that the difference is less than 3%. So that's the only error. So if you are okay with living with that 2 to 3% error, then you don't need to take any more. And then again use the stress strain relations, put in the stress expressions here, use the strain transformation relation, and then I come up with this big looking expression again for the strain value as a function of all of these angles here, okay, and all these other terms. Now these terms become a little more involved because in the isotropic case, each direction was the same. E was the same. Now you have E, N, E, new where T, and so on. Okay. So that's the only thing that you have to keep track of more terms here. And then very similarly, we again get K1D equal turns out that when you try to put the boundary conditions and you try to simplify the expression so that you are left to find these constants A, and there should be some of this constant A in these different terms. You can, if by manipulating the angle of the gauge, as we saw in the isotropic case, by manipulating the angle of the gauge, you can have some of these terms drop out to zero. Okay, so it's just a simplification procedure. And it turns out in this case, there we saw that cosine 2 alpha equal to minus Poisson's ratio was that criterion. Here in this case of the orthotropic material, we get tangent square phi is equal to 1 over mu LT. So again, you use very similar thing. You put a gauge here at a certain angle, and then you can use these type of samples. Again, put gauges, obtuse and acute angle gauges. And this is what we did. So we made a glass fiber epoxy composite. And now we went to epoxy because we actually bought pre-pregs and we put them one on top of the other, 10 layers, and hot pressed them. Okay. And so 10 plies, hot pressed at 140 degrees C for 30 minutes. Glass fiber volume fraction was 40%. Strain gauges were 120 ohms, 2.5 millimeter gauge length. Okay. And then the composite properties are given here. So nu LT value is 0.32. So for this nu LT, use tangent square phi equal to 1 over nu LT, and then you get these two, 60 degrees, 60.5 and 119.5. And just run your experiments again. Alright. Now using those expressions that we have, we can plot some things like as a function of the crack tip, what is your strain output for an assumed crack velocity. So it turns out now that for acute angle orientation, I get zero, almost zero output for when the gauge passes through the center of the, when the crack passes through the center of the gauge. But for obtuse angle, again I get peak values. So that's the only difference. So I can get, okay, here. So an averaging error. So all of this that we did is for one point, the center point of the gauge. But the strain gauge is 2.5 millimeters in gauge length and about 1 to 1.5 millimeters in width. So it's a little more finite system. So what happens, so you can now actually using your equations, you can try to simulate what happens if I take a grid. So I have 2.5 millimeters by 1.5 millimeter grid on the strain gauge. So I can take different points and try to calculate what is the error from the center point. If I try to plot that, I get the averaging error here and the crack tip position on this side. We see that we get this type of a curve. Okay. So let's see what happens here for the obtuse angle gauge. For the obtuse angle gauge, for the crack tip position of 0, that means the crack is right underneath the center of the gauge. What is the averaging error? Is 0. So that's a big advantage of using obtuse angle gauges. Here, there is no such, I cannot draw any conclusion like that. It just goes up and down and there's nothing I can do. This is the type of strain profiles that we see coming out from our measurement. And then I go, if I put different gauges, like 4 of them, track velocity 250 meters per second, obtuse angle gauge at a height of about 6 to 7, 6.5 to 7 millimeters. This is the strain output. This is as the crack is growing from 0.45 to 0.7 A by W. We always write A by W because it's like a non-dimensional number, crack length divided by the width of the sample. And then KW is, K1D is 1.8987 to 7.8. So what you see here, that the crack is progressing with almost a constant stress intensity factor. Not much change. We see this little jump here. Okay. And you also see this jump here in the strain value. Why do you think that jump might be? What happened at gauge number 3? Sorry? No, it's most likely it is, see, so what happens, think of this. Now I have the sample, I'm pulling it, then suddenly the crack begins to move. It achieves critical stress intensity. When it suddenly begins to move, now it is, and the crack is going all the way through at a very high speed. So it's unloading and all the strain energy is certainly given out, some of it in sound, so you hear a loud sound. Some of it is given out as waves. So there are a lot of waves which are given out inside the material. And those waves then go and reflect and come back at random. So most likely a reflected wave came right at that strain gauge location when the crack tip was passing below. It's just random. It could have happened here. It could have happened here. So it's just a wave reflection that came back and gave you some extra strain at that. And then just one more for a little higher crack speed, and we see that again the values are very close. So that's another way to look at, if you want to study some fracture things, you can easily do it by using strain gauges. You'll find strain gauges everywhere. We use it all the time. So it's a very simple and cost-effective method for finding a fracture parameter, which is K1, which is the most important parameter. Okay, if the crack is not going straight, so if it is curving, then that means that you have a little bit of, you still have K1 loading, but you also have some amount of K2. So if it is going in a curve, then so your output from the gauges, the way we have designed our expressions and everything, is as if it is K1. So your output from all the strain you measure and everything will give you K1, whereas it is not your K1. So there will be some errors in it. So it will be hard to find. You cannot find K2 using strain gauge. Huh? Yes. So that's why I said you make that little V notch on the back side. So what you will do is basically this, what I was saying, that you have the sample. have this sample. So I have, so let's say that's my sample. So what I'm going to do is, and I put my gauges here. These are the strain gauges on the back side. So I create a little notch on the other side, which is running all the way to the other end, and that will help to guide the crack through in the straight along a straight line.
So in the straight gauges, how much the distance will be from the center?
That is, remember we did that, like how far away, that depends on the singularity dominated zone. So if you have like in the modified compact tension specimen, the singularity dominated zone in the obtuse angle direction was about 10 millimeters, but in the acute angle direction it was only 2 millimeters. So as long as I put my total gauge is in the singularity dominated zone, you can put it anywhere. But you don't want to put it too close to the string, the crack tip. You don't want to put it like 1 millimeter away from the crack tip or half millimeter, because then, as I said, that very close to the crack tip, the stresses are three-dimensional in nature, and there's plasticity there going on, and then in the composite you have delamination of the fibers going on and so on. So there is all sorts of things happening. So you have to find just a sweet spot where you're not too close or not too far, but you're in that singularity dominated zone. So that was just my intent to give you a little flavor that yes, you can work through all these different expressions first, come up with an equation for strain in terms of the wave speeds and the properties of the material, and the strain output from the gauge. And then you can find the stress intensity factor. Yes. See, the crack does not distinguish between whether it's aerodynamic loading or it is some other mechanical loading or whatever, wherever the load is coming from. So because of aerodynamic loading, you need to know what is the load on the crack surface. So if you have this big plate and in the middle there is a crack somewhere, you need to know what is the opening, the stress is trying to open the crack. How that stress is being created, the crack doesn't care. The crack only cares what is the level of stress, or what is the type of stress, say opening mode, shear mode. Can be interpreted what? Yes, you can. People have done that. So in the bioimplant, you can have different. You can maybe do a finite element simulation. That's what I was trying to do. To find the nature of the stress field. For example, in that figure, ball head. And then you can, and if there are cracks So as long as you know what is the dimension of the crack, what is the orientation of the stresses on the crack based on whatever application you have, then you can figure out whether it's mode 1, mode 2, mode 3 or a combination mode. It can be all three together, K1, K2, K3. Then you work out whether it will fail catastrophically or not by comparing it with a critical stress index. Okay. So whether the load is coming from a bio-implant application or a wing of an airplane or a cricket bat, it doesn't matter. Like Rohit Sharma, he broke his back. So obviously it's a crack which has started, and so it had a sensor in there. So the cracks, when they start to grow, they give out. So as I said, whenever a crack grows, it suddenly gives out energy, right? So it goes as a wave. So if you have an acoustic sensor somewhere, and if suddenly you see like the stress waves coming, that means there is a crack beginning to grow. So you can make some money by introducing an acoustic sensor and cricket bat, which figures out, okay, it's going to rain. Okay, well, it seems that people are ready to go.